It is our tradition already, maybe 7 years, that the last session in the spring semester is devoted to the talks of young participants or students from different universities. And we have a hope that after several years, the speakers became to be mathematicians who will participate our seminar frequently. It is my pleasure to announce the first speaker today. He is Daria Kalytiuk from National Technical University of Ukraine, and the talk is named Complexity Indices for Random Graphs. Please. Daria.
Yes, a minute, please. I will demonstrate my screen. Could you see my screen?
Yes.
Great. Good afternoon, dear colleagues. My name is Kalytiuk Daria. My supervisor is Iryna Nishchenko. And today the topic of my talk is complexity indices of random growing graphs. It is well known that random graph models are widely and successfully used to study phenomena and processes arising in various fields of biology, ecology, chemistry, sociology, computer science, and etc. And therefore, there is a natural need to be able to quantitatively describe the complexity of such structures modeled by graphs, that is, to introduce an appropriate topological index. Let's start now with a little historical introduction. In 1947, the Austrian-American chemist Harry Wiener proposed the first topological index of a molecule, defined as the sum of the distances between any two carbon atoms, and called it the path number. This index later played a significant role in modeling many physical and chemical characteristics of alkane molecules. Wiener himself noticed the correlation of the path number with critical boiling points. In 1976, correlations between the Wiener index and such characteristics of a substance as viscosity, density, and surface tension were demonstrated. And in 1979, a correlation coefficient of 0.999 between the Wiener index and the chromatographic retention time was achieved. Subsequently, the question about possible ways to calculate Wiener index efficiently inevitably arose. It turned out that for trees, an example of which is the structural formula of alkanes, it is calculated most efficiently, i.e. linearly. However, in modern graph theory, Wiener indices are also considered for cyclic graphs of a special kind. Moreover, with the expansion of the range of tasks, there was studied various generalizations of the Wiener indices, which were called Wiener-type indices. So let's denote the tree on n vertices as Tn and d as the distance between any two vertices in this tree. So now we can define the Wiener index as the sum of such distances within unordered pairs of vertices. One of the most fundamental properties of the Wiener index is that it characterizes the branching of a tree. The index value for a tree of arbitrary shape always lies between the index value of a tree of diameter 2, which we call an asterisk and which we assign as Sn, and a tree of diameter n-1, which we call a chain and assign with Cn. Talking about a random graph, the marginal distribution of the Wiener index and the asymptotic behavior with expected value depend on the way the graph is constructed. In our work, we consider two different models. The first one is a special modification of the generalized Erdős-Lee model, in which edges grow uniformly and independently of each other, then and only then the adding an edge does not lead to the cycle formation. The second model is a so-called uniform recursive tree, which grows from the root, the vertex labeled with 1, by joining the next numbered vertex to a randomly selected one. For our convenience, we will denote the first tree model as Tn, and we will call it random growing forest, and the second model as Tn with upper index rec. So let's start by looking at the first model. When introducing the new index, we were guided by the following goals. Firstly, the new index, like the -1, should characterize the branching of a tree. Secondary, we want the index to be applicable to the disconnected tree, i.e. forest. And thirdly, we want the index to be multiplicative. Thus, we came to the following form of the complexity index of random growing forest. It is the sum of exponential function of the negative distance value, where the summation is performed over all ordered pairs of the vertices in the tree. We can also define such a variable dk, which denotes to the number of ordered pairs of vertices in the tree with distance exactly k between them, and rewrite the complexity index definition the next way. This form lets us easily calculate complexity indices for a chain and asterisk trees on an arbitrary vertices number. Since we are considering a random tree, the value of the complexity index of such a tree is a random variable too, and thus we are interested in its distribution, namely the expected value. As we have already noted, the complexity index characterizes the branching of a tree, which can be shown by mathematical induction. Let's do it now. Let Tn be a tree with a minimal complexity index. Then the difference between two complexity indices of tree on n+1 vertices and n vertices can be expressed the following way. It's obvious that attaching next vertex to such vertex E with asterisks that minimize given value epsilon would form a tree on n+1 vertices with minimal complexity index 2. So the first step of the proof is a base case. For n equal to 3, we have only one tree. For n equal 4, we have two different trees, one asterisk and one chain, and we can easily check that the difference between their complexity indexes is greater than 0, as we want it to be. On induction step, we assume that complexity index for an arbitrary tree is not less than chain complexity index for any vertices number. Then the minimum epsilon value would be calculated the following way, and so we can rewrite the above difference, and to make sure that it's actually the difference between two chain complexity indices, which proves that complexity index is bounded from below by chain complexity index for every n. And same way we can prove that complexity index is bounded from above by asterisk complexity index. Finally, we can assert that due to property of monotonicity of the expected value, it has the same boundaries as the index itself. And moreover, as we can see on the following plot, the expected value is always closer to the lower bound, and so that is the bound we would try to improve. As we previously mentioned, when considering random trees, there is a need for an intermediate estimation of an unconnected tree, i.e. a forest. So let's denote a random forest with k edges the following way, and let's define a sigma algebra generated by the set of all forests from previous time moments of growing this random tree. We can apply the complexity index to random forest if we set the distance between vertices from two trees in a forest equal to infinity. Now let's assess chain complexity index with a linear function. We would need it later. If we consider the forest with k+1 edges being formed from forest with k edges by growing in it one particular edge, let's name it E, we can express the forest complexity index in terms of complexity index of the previous forest the following way. Then, taking conditional expectation, we can see that here in the numerator, we in fact have a product of two complexity indices, which, as we recently proved, we can assess by chain complexity indices. Using this linear estimation for chain complexity indices, we can assess this summation the following way. The summation in the denominator we would bound from the above, and after all substitutions and reductions, we would take an azimuth expectation and get the following lower bound for an arbitrary random forest expected complexity index. If we substitute here n-1 instead plus k plus 1, we would get an improved lower bound for expected value of complexity index for the random tree, starting from the number of vertices equal to 17, and as we can see this on the plot. And the same inequality leads to the following asymptotic lower bound for the normalized expected value of the complexity index. The next question we will consider is how does the complexity of a tree depends on the complexity of the connectivity components of the forest from which it grows. It turned out that forests formed on disjoint subsets of the set of vertices of a random forest are independent. Formally, it can be written the next way. Let's now describe this formula. Let's divide the set of n vertices into two disjoint subsets of dimension m and n-m respectively. So the probability that at some moment forests D1 and D2 with K1 and K2 edges will grow on these subsets, conditional to the fact that at some moment a forest with K1 plus K2 edges was formed on n vertices, and this forest can be split into two forests with K1 and K2 edges on m and n-m vertices, is equal to the product of the probability of growing forest D1 on an isolated set of m vertices, and growing a forest D2 on an isolated set of n-m vertices. We will prove the theorem by mathematical induction. On the base case, let's assume the following initial conditions. It's obvious that the probability of getting forest with no edges equal to 1, and the probability of getting forest with one exact edge is equal to 1 divided by the number of all possible edges in graph on m vertices. For the left part of equation, we can write out the conditional probability, and being followed by the same considerations, find out that this quality is really holds for given condition. Let's switch to the induction step. Here we assume that the equation is true for any non-negative K1 and K2, which gives us L in total, and we need to verify if it would be true for such K1 and K2, which would give us L plus 1 in total. Here we would need to write out the probability of obtaining the forest D as the sum of probabilities of obtaining all possible previous step forests, if forest which we can get by removing one edge from forest D. And then we would need to introduce also two hypotheses that distinguish on which of two sets the L plus first edge would be grown. And then with few intermediate steps, we would come to the following equality and finally finish proving the theorem. Now we can derive a recursive formula for complexity index. Among all the ways to construct the tree Tn on n vertices, we consider only those in which at the penultimate step there were two trees, Tm and Tn minus m on m and n minus m vertices respectively. And we would denote this event of growing such a forest as an uppercase C. Given that the indicator of this event is measurable with respect to the sigma algebra generated by this event, we can assess expected value of the complexity index the following way. The next expression for the complexity index we have already seen while deriving lower bound on the previous slides. Then we take conditional expectation and using previous result about trees independence, get the following assessment of expected complexity index in terms of complexity indices of trees on penultimate step. Now, consider the model of a uniform recursive tree. Given that the vertices in this tree are numbered, the complexity index has been modified. Namely, here only the distances from the vertex to the root of the tree are considered. And as it was with the previous one, this index we will also rewrite for our convenience with the similar way, considering the random variable dr with asterisk, which denotes to the number of vertices which lies on a particular distance r to the root. To derive the expected value of complexity index, we would need to express this variable in a recursive way, and also to consider the sequence of independent and identical distributed random variables sigma k, each of which indicates to what vertex the vertex number k is going to be attached. Considering also the sigma algebra generated by this sequence, we can find the conditional expectation for variable dr with asterisk, and to use it then to find conditional expectation for complexity index itself. And then taking another expectation and iteratively revealing the formula, we would finally get the expression for expected value of uniform recursive tree complexity index. Here, gamma is denoted to gamma function. From this expression, we can find the constant to which the normalized value of the expected, to which the normalized value of the expected value of the complexity index approaches when the number of vertices tends to infinity. And it can also be shown that the natural logarithm of the expected value behaves like a linear combination of two generalized harmonic numbers. And finally, we present a theorem on the asymptotics of the complexity index of a random recursive tree. Firstly, when we derive the formula for the mathematical expectation, we could ensure that the given sequence of random variables forms a so-called martingale. Further, we can show that the expected value of the square of complexity index can be bounded from above by this expression, and so the square of the the expected value of the square of this random variable does not exceed 2, and thus according to the martingale convergence theorem, this random variable converges almost surely and in quadratic mean. And since convergence in quadratic mean leads to convergence in mean, we obtain equality of the limit of the expected value of the normalized complexity index and the expected value of the random variable to which it converges. And that's all. That's the end of my topic today. I'd like to say that I appreciate the opportunity to present here today, and thank you all very much for your attention, and you're free to ask any questions.
Thank you very much for interesting talk, and maybe somebody have comments or questions, please. Daria, can you say something about asymptotics of other Wiener indices? Do you know some results about the asymptotics, and can you compare its asymptotics with this one?
Honestly, I haven't seen enough research about asymptotic behavior of Wiener index itself, so I'm not sure that I can answer this question now.
Because it seems that since we have at least small conclusions that this multiplicative index reflects some complexity, some branching complexity of the tree. Maybe if we have some asymptotic, we can make conclusions that our random tree is not branching is not very rich in branches. Yeah, it will be interesting to see and even to look for some nature for some applications For example, when we consider growth of dendrites, then it is very interesting to understand the structure of branching. I think that such comparison with initial winner indices and with the problem which we have in applications can be interesting and useful for further studies, if you plan to do this.
I agree.
Okay. We actually plan our conference in the mini conference in such a way that we have some time for discussions. I propose to keep the schedule of the conference, and the next talk will be exactly as I think in 8 minutes. So let's wait. Let's continue. Let's continue our session, and the next speaker is Valeriya Kotelnikova. We know her very well because she already gave talk not only on the Skorokhod readings, but also, so how to say, uh, like talk as a regular scientist at our regular session of the Malayan calculus and applications. So I think that Valeriya can be a very good example for other participants today. I must say that they are also welcome to make a talk, 1 hour talk at our seminar. Okay, Valeriya will give us talk on the subject law of the iterated logarithm for iterated random walks with application to random recursive trees. Please.
Mm-hmm. Thank you so much for the kind introduction, for those kind words. And hello, everyone. My screen is still loading, as I can see.
Oh, here is.
Yes. Okay. For some reason, my laptop decided to be very slow and to freeze. Okay. Again, hello, everyone, and I want to thank to Andrey not only for the kind words, but also for keeping the tradition of the Skorokhod readings alive, because it's very important for students who just start their scientific journey to have some place where they can share their results and not being judged from the level of high-level scientists. So my talk is based on recent joint paper with my advisor Sasha Iksanov from Taras Shevchenko National University of Kyiv and Zahar Kaplutchko from University of Münster. And here the talk is going to be split into 2 parts. First, we are going to talk about iterated random walks and law of iterated logarithm for those walks. And in the second part, we are going to apply this law of iterated logarithm to random recursive trees. So let's start, and we start from introducing some notation for standard random walks. So by xi, we denote almost surely positive random variable, and by xi1, xi2, and so on, we denote its independent copies. Then by Sn, we denote standard random walk with increments xn, so that Sn is just the sum of xi1 and so on xn. And the process we are interested in is the renewal process, which we denote by y. And it is defined as the counting function for sequence Sn. And also we are interested in the mean of process y, which is denoted by v, and this function is called renewal function. Now let's recall a construction of a general branching process generated by standard random walk S. And sometimes it is also called Crump-Moe-Jagers process. Everything starts at time 0 when there is the ancestor who resides at 0 generation. It initiates the whole population. And then the rule is the following. An individual born at time t produces offspring with birth times which have the same distribution as t plus s, where s is the standard random walk. So let's look what is going on. Ancestor born at time 0 produces children with birth times s1, s2, and so on. Here they are. Then let's take one of its children, individual born at time s1, and it produces offspring with birth times s1 plus s tilde. S tilde is independent copy of standard random walk S, and those children are marked here in blue color. Then let's take another individual born at time s2. It produces offspring with birth times s2 plus s hat, where s hat is another copy of standard random walk S, which is independent of both of S and s tilde. So by this independence, I forgot to say that all individuals act independently. That's why those s tilde, s hat, s should be independent of each other. And the kids of this individual are marked in green. Offspring of individual born at time s3 are marked in red, and so on. And we say that individual resides in the kth generation if it has exactly k ancestors. So those blue individuals live in the second generation because they have 2 ancestors. One is the individual born at time s1, and another is the ancestor of the whole population. And let's denote by yk the number of individuals from the case generation which were born up to time t. And by vk, the mean of this process yk. Then yk can be thought as a generalization of the renewal process y. Because if we take k equal to 1, we have the number of individuals from the first generation which were born up to time t. And since the birth times in the first generation are S1, S2, and so on, it is exactly the definition of renewal process y, and therefore V1 is the renewal function V. And let's denote by Sk the birth times in the case generation in arbitrary order. Then this sequence Sk is called an iterated standard random walk. And before stating our law of iterated logarithm for it, let's overview some important results which have already been known for iterated random walks. I'm going to mention the limit theorems, which are pretty close to law of iterated logarithm, or some auxiliary results which we were using in our paper. To do that, we denote by D the Skorokhod space of Kalytiuk functions on the negative half line. And by fancy word Kalytiuk, we mean that the function is continuous from the right and has finite left limit. The first result is from 2018. It's from paper by Iksanov and Kalytiuk, my co-authors, where they have proven a functional central limit theorem for process yk on the Skorokhod space to the power n, equipped with the product G1 topology. And they have proven it under the assumption you see at the slide. A bunch of other results is due to a recent paper from 2023 by Iksanov, Rashitov, and Samoilenko. They have proven there a lot of different results, but we want to state only 3 of them. First is that for fixed generation K, they have found an asymptotic behavior of the variance of process yk under 2 assumptions, which you can see at the slide. Then the behavior of the variance is some constant times t to the power 2k minus 1. Another result, which was important for us, is an analog of the elementary renewal theorem. So they have found asymptotic behavior of function vk at infinity, under the sole assumption that the mean of psi is finite. And the third result I want to mention is the counterpart of Blackwell's theorem. So they have found an asymptotic behavior of the difference of vk at t plus h and vk at t for arbitrary positive h, under assumptions you can see at the slide. And of course, those are not all of the results proved for iterated random walks. In particular, there are a lot of results proved when generation k is not fixed, but it is dependent on time t. However, we do not mention those results because our law of iterated logarithm is for fixed generation k. And before stating it, let's establish that by 0 factorial we mean 1, and for family of real numbers xt, C stands for the set of its limit points.
Valeriya, can
Yes.
I ask you the following? I understand that maybe you follow some special technique which is already produced and is regular for renewal theory. But what if we consider this iterated random walk just as multiple triangle sums of independent random variables? You see? So the first one is the sum of the order 1, the second one is the sum of the order 2, but when indices are when indices are ordered and so on. Is it similar to what you consider? Because then at least result about the asymptotic of the y expectation of yk is very expectable. Yes, it is a partial part of the exponent. Yes, so is it related to because there are a lot of limit theorem for triangle sums of independent equidistributed random variables, and it is a very popular branch of statistics.
Okay, let's go back to this picture here. I have never seen triangle sums, but from what I understood, so we have like first read variable s1, then we have s1 plus s1 tilde, then s1 plus s1 tilde plus something else which is independent and so on, yes?
Yes, and on the next generation, you will have S1 plus S1 tilde plus S1 plus, for example, S2 with 2 tildes and so on, yes? And this exactly is a triangle sum if we have just independent summands, yeah? Why
Okay,
not?
okay. Yes, okay. If we take just this sequence, yes, it looks like it's triangle sum. And like, is it another triangle sum when we start from individual Born times?
We just are looking for such partial sums of this triangle, so-called discrete integrals, which are less than t, and then look for asymptotic. At least I think that it is connected to such object in statistics, and at least it can be helpful to have a look. Yeah.
Okay, I've never seen triangle sums.
Point of view, it is, as I said, very natural to say, okay, the asymptotic of the mean will be the following, yeah, like the part of exponent. Yeah? Okay, let's go further.
Yeah, but it's a good suggestion. I think after my talk, I'll take a look at how triangle sums are precisely defined, and I will see whether they may work here.
But let me say a few words. But this, could you please scroll back? Yeah, but here the random variables are dependent, say S1 and S2. So these points of different colors and points of the same colors are not independent.
Yes, surely, I understand, but these variables are the sums of independent summands, and we at each row we have independent summands like size with tilde, size with 2 tilde, size with 3 tildes, and so on. And we just organize such a sum where we use something from xi, something from xi tilde, and so on, and just left for the first moment when we just hit level T, for example. Yeah. So I think it can be just another point of view, and my question is that maybe it can be helped. Just this is a comment.
We'll take a look at it, but just as a comment, the number of individuals in the second generation, which are located to the left of T, is just a convolution of the mean number of the individuals in the third generation. And the same for each generation. So the mean number of individuals in the kth generation, which are located to the left of T, is a k-fold convolution of the mean number of generations in the third, of individuals in the third generation. Okay.
Okay, thank you. Okay, let's go further.
Yes, okay, this one. What? Okay, I stopped here. So our law of iterated logarithm we obtained is the following. Denote by sigma squared the variance of xi and assume it is finite. Then for each fixed generation k, we have shown that the set of limit points of process yk centered and normalized in a proper manner is equal to -1, 1 almost surely. And here in the normalization, we see constants ak, which are defined in such equation. And by sigma, we denote here the square root of variance. And by mu, we denote the mean of xi. And in particular, of course, it means that the upper limit is 1 and the lower limit of this fraction is -1 almost surely. And another important result, a remark, is that the centering here can be replaced with more intuitive, which is the mean of process yk. And let me explain you why. First of all, due to aforementioned result from paper by Iksanov, Rashitov, and Samoilenko, the mean of yk is asymptotically equivalent at infinity to the center in which we have chosen. However, there was no result about the asymptotic behavior of difference of those two functions. So in our paper, we have proven an auxiliary lemma in which we have shown that the difference is bounded by t to the power k minus 1. And since the denominator here is growing faster than t to the power k minus 1, you can choose the center in which you like. It's just up to your taste. Now we move to the second part of talk, where we are going to apply this law of iterated logarithm for iterated random walks to the profiles of random recursive trees. And before defining random recursive trees, let's first define deterministic recursive trees. So by deterministic recursive tree with n vertices, we mean a rooted labeled tree with labels 1, 2, and so on, that adhere to 3 following rules. First is that the root is labeled always with 1. The second rule is that the labels of vertices on a path from the root to another vertex down the tree form an increasing sequence. And the third rule is that the vertices labels at fixed level increase from left to right. And by the level of vertex, here and after, we mean its distance to the root. And let's picture all of possible deterministic recursive trees which adhere to those 3 rules for 1, 2, 3, and 4 vertices. For 1 and 2 vertices, there exists only per one such tree. For 3 vertices, there exist 2 such trees. And for 4 vertices, there exist 6 such trees. And let's follow those rules for those particular deterministic recursive trees. As you can see everywhere, the root is indeed labeled with 1. Then by the second root, we mean that if you take some path, for example, here, 1, 2, 4, from root to the last vertex in this path, the labels form an increasing sequence. And it is indeed true for all of those trees. And by the third rule, we mean that if you fix the level and you go from left to right, labels increase there. So like here, 2, 3, 4. We are interested in how many deterministic recursive trees on n vertices exist. When you have deterministic recursive tree on n vertices and you want to add n plus first vertex, you can add it in a unique way to one of already existing. Therefore, we obtain such recursive equation. After solving it, we figure out that the interested number is n minus 1 factorial. And with this at hand, we move to the definition of random recursive tree. So random element Rn is called random recursive tree on n vertices if it is chosen uniformly randomly from all possible deterministic recursive trees on n vertices. And how to generate such random recursive tree? At step 0, use...
Valeriya, can I ask you, it is interesting question usually how to produce some random object when we have a set of non-random graphs, in your case trees or so on. Because you see, can it happen that the same tree from your set can be built in different ways?
Can be viewed in different ways?
Can be built, can be constructed in different ways, or not? Or there is only unique way to build one deterministic tree?
If you mean by construction, the construction about which I'm talking now? No? Yes. So then the tree can be constructed in the unique way, yes.
Oh, in unique. Okay, then this is natural, because if not, then maybe another probability distribution will be more natural, yeah?
Maybe.
Okay, good. Thank you.
I'm sorry, I have another question. So when speaking about random recursive trees, these are trees that are generated according to this algorithm? Exactly, right? So this is like a definition of them.
The first, the definition is like first sentence, and then it's just a way how to generate it. So have to understand the process of having random recursive tree. Okay.
I don't understand the definition. What is R1Ns?
I barely hear you. I heard something about.
Okay.
Okay. Yeah. Sorry, I didn't hear you. So at step N, from the previous step, we already have random recursive tree with n vertices, and we want to add the n plus first. And we can add this n plus first vertex in the following manner. So you pick one of already existing nodes, you uniformly at random, and add the new node to one of existing.
Mm-hmm.
And let's define the profile of the random recursive tree for which we want to prove the law of iterated logarithm. So denote by xn of k the number of vertices at level k in a random recursive tree with n plus 1 vertices. It may be a little bit confusing why we write index n and yet we mean n plus 1 vertices, but the index here refers not to the number of vertices, but to the step in the generating algorithm. And then such function is called the profile of random recursive tree. And we can calculate the profile for such a recursive tree. We write here index 3 to show that tree has 3 plus 1, that is 4 vertices. At the first level, the value of the profile is equal to 2. We have there 2 vertices. At the second level, we have 1 vertex. And at the third level and further levels, we have 0 vertices. And now we move to the part of talk where we discuss how to connect iterated random walk and random recursive tree. And the idea how to do it is not ours. It is already 30 years old and it belongs to Peter. And the idea is to embed a random recursive tree in the general branching process. Shortly, what we are going to do, we take general branching process, we build a tree on it in some specific manner, and then we prove that the obtained tree is a random recursive. So let's start doing it. We take in the general branching process step xi not arbitrary anymore, but exponential with unit mean. And then by ascend, as previously, we denote the corresponding standard random walk. We take the iterated random walk as k and treat it now as the burst times of the vertices at level k of our random tree. So here we have a picture which we had for general branching process, and we start interpreting individuals there as vertices in a random tree, and we label them chronologically as they appear. So the ancestor corresponds to the root of the tree. It is vertex number 1. Then the second individual to appear here is individual born at times 1. So it is vertex number 2 of random recursive tree. Then the third individual, which appears here, corresponds to the third vertex. And we have a candidate for the fourth individual to appear, so for the fourth vertex. But we do not know whether it's exactly it, because we know nothing about the child of vertex number 3. Maybe it is born earlier. And let's denote by tau n the time at which we add vertex with number n plus 1 to the tree. So let's calculate burst times for first 3 vertices. The burst time for vertex number 1, it's tau 0, and it is always 0. The burst time for vertex number 2, tau 1, it is always S1. However, for the vertex number 3, the burst time has more complicated expression, and it is connected to the fact that depending on which value is smaller, either the burst time of the second child of the root or the burst time of the first child of vertex number 2. Then we can end up in 2 different situations. And exponential distribution with unit mean mean was not chosen out of the blue because due to the memoryless property of exponential distribution, the obtained random tree has a feature that each new node is attached to one of already existing one uniformly at random. And having this at hand, you may prove that a random tree obtained at tau n during this process has the same distribution as the random recursive tree at time n+1. And this is the key to embedding process. And last step we are left to do is to understand how the profile is connected to the process yk, for which we already have the law of iterated logarithm. Let's think about profile in terms now not vertices at levels, but individuals at generations. So xn of k can be thought as the number of individuals in the fixed generation k, which exist at time tau n. And it is exactly the definition of process yk at time tau n. So this is basic observation which holds almost surely, and it is the key to our proof. And before going to the law of iterated logarithm which we obtain, let's overview some results which have already been known before us. So first bench of results is from paper from 2006 by Fuchs, Hwank, and Neininger. They have found there for fixed generation k the asymptotic behavior of the profile, the variance of the profile, and they have proven a central limit theorem for the profile. Then there was aforementioned already paper from 2018 by Iksanov and Kalytiuk, where they have generalized the result by Fuchs, Hwank, and Neininger by proving a functional central limit theorem for the profile. And now we are ready to state our law of iterated logarithm. So we have shown that for each fixed generation k, the set of limit points of xn of k, centered and normalized in proper manner, is equal to -1, almost sure. And okay, I still have some couple minutes. So I want to mention that our law of iterated logarithm for k, which is equal to 1, is not new. It is already known. However, as a result for k, which is at least 2, is completely new. And I wanted to explain where do we know this statement, but honestly, looking at the time, I don't think I will make it. So I will stop at this.
Yes. Okay. Thank you very much for interesting talk. Actually, some comments and questions were already were discussed. So I think that we have just 1 minute for one short question.
Thanks very much.
Nikolai, you can print your question, yeah?
Yes, please.
Valeriya, oh, okay. Yeah.
Can you show the previous algorithm slide again, please? Of course I can.
Mm-hmm.
This?
No, definitely not.
Maybe the definition of this recursive tree. Mm-hmm. Okay. Okay. Unfortunately, we have no time for discussions, but I hope that Valeriya will join our seminar maybe at fall semester, and we will have a possibility to discuss everything. Valeriya, thank you again, and we have to go to next talk. Thank you very much. Our next speaker is Nataliia Monina, now from University of Ottawa, but I think she began to work with this with the topic of the talk, maybe here with Georgy Ryabov, and continue to work with Augusto Gerolin. So the title of talk is Classical and Quantum Optimal Transport. Please.
Okay, thank you very much for the introduction. So I'm gonna open my slides now and then also say a few words about myself and also tell what the talk is gonna be, how the talk is gonna be organized. So I'm Nataliia. I'm a PhD student at the University of Ottawa, and so my research is on classical and quantum optimal transport. So I wouldn't say that this talk is very related to what we saw so far. So it's not very deeply related to stochastic processes yet. I mean, this is not exactly what I'm working on currently, but it's more related to measure theory and real analysis. And so there are some nice connections actually with stochastic processes, but I'm not going to touch this topic. And yes, so let's look at the overview of what we're going to talk about. So it's the first I'm going to actually define what is optimal transport, why is it important, what do we actually do in this whole thing, and yeah, like where do these problems arise. Then I'm going to talk about the solution techniques. So like I'm going to illustrate it on a specific example, which is related to the discretization of some optimal transport, because it is something that is usually considered for continuous distributions or generally, but if you want to solve it numerically, you always consider some discretization, and anyway, you will have to also, the discrete example will give you some nice intuition about like how this whole thing is going to work. And later, I'm going to introduce the quantum optimal transport, or like what it is, how it is related to the classical optimal transport, and like what are the results that we actually can translate directly to the from the classical theory to the quantum theory, which is non-commutative. And then in the end, I'm going to briefly talk about my PhD research. So what am I actually doing? So this talk is not really going to be about my results. So like my results are in the papers, but I'm going to just talk about the topic and why is it important. Okay, so let's first define what is optimal transport. Well, optimal transport is just the class of constraint optimization problems. So we have some, and these problems are defined usually on some joint distributions. So we have some measure spaces, and we have some prescribed measures on these spaces. So we consider mu and nu as just probability measures on X and Y. And then we also usually use some cost function, which is just a function from X times Y to R. We usually say it's bounded or lowest semi-continuous, so it has some nice assumptions. And we want to minimize some functional. And the typical functional that we want to minimize is the integral of this cost function with respect to the probability measure that is a joint probability measure on the spaces X and Y. However, nothing in this world is very simple, and this measure has to satisfy some marginal constraints. So the marginal constraints in this case are such that if you integrate this measure with respect to one space, you get the first marginal measure, which is measure mu, and if you integrate over the other space, you get the second measure. I'm sorry, let's see. Okay, it's not the questions for me anyway. Sorry. So basically, this whole problem can be defined in such a way that you minimize over some convex set, and this convex set is the set of such probability distributions on X and Y that have its projections equal to these marginal distributions. So the famous Kantorovich problem is defined as the infimum over all of these possible measures of this integral. Okay, it doesn't work. Okay, now I'm gonna talk a little bit about where these problems can arise, or like how it's important. So when you take a specific cost function that is the distance to the power p on the spaces of, if you take the same space like X and Y, then this optimal transport that you find on the previous slide is actually the p-Wasserstein distance, and this is the distance between the measures. So what is nice is that we also know about measures, that we have some convergence in distributions and so on. But what is nice about optimal transport in here is that it actually meterizes the weak-star topology. So it has some nice properties. It considers the geometry of the space of measures. And for example, here in this picture, you can see that, so if you take, like, for example, two Gaussian distributions, and you try to take some interpolations, and the first, in the picture A, you take the interpolation with L2. So it's gonna somehow construct one measure from another one in the L2 sense, where you kind of measure vertically. And if you take the interpolation with the Wasserstein distance, it actually looks like a more natural interpolation, so that it actually considers the geometry of the space.
Natalia, am I right that your interpolation by Wasserstein distance means that you want to go like in through the geodesic line in the Wasserstein space?
More or less, yes. So it is one of the ways to view this approach. But you can also take some middle point and consider a Wasserstein barycenter. So in this picture B, you're not solving the continuous problem on in the space of geodesics, but you're just taking some inner point, and you're solving two optimal transport problems, so that you want to minimize the one that is in between these two, or the one in between these two.
Okay.
And you're taking their sum. Okay, so there are also several applications, optimal transport theory in economics, meteorology, geometry, fluid mechanics, engineering, and so on. And another one that is actually quite relevant to my research group is the applications to quantum chemistry, and more or less the density functional theory. So there are some problems in some energy minimization of some system of electrons. And it is relevant when you take the cost function that it has a form 1 over the distance between the points. So it's relevant to the potential energy, for those who know this kind of, or for people who are familiar with potential energy, some Schrodinger equations and so on.
Natalia, excuse me. So if mu equals mu, then this is infinite.
Yes, this is very interesting. So in particular, in the quantum chemistry case, you generally consider that your electrons have the same distributions, but if you consider this potential energy, you want to see how the system actually evolves and what is the best configuration of the system, and your electrons actually have to move. So for the same distributions, this is exactly the point that we are interested in the quantum chemistry case.
So this 1 over dxy is like potential in Dyson diffusion. Yes, they're repelling.
Yes, exactly. So this is the potential energy of the interaction of electrons. So we have the force, so there is a repelling force of the electrons, and it's the potential energy that produces this force. Yes, so now let's talk about the motivation and how of the possible approaches on how to solve optimal transport. And I'm going to illustrate it on the example with the discrete optimal transport. So for discrete case, I'm going to consider some point clouds. So I have measures that are just situated on some points. And then I can associate the cost function, which in this case can be represented as a matrix. And the optimal transport problem in this case is the minimization of this integral of c with respect to the pi, but the pi can also be represented in terms of a matrix. So it can also be discretized, and you get sort of a linear functional in terms of pi with some coefficients that are Cij. So in this case, these marginal distributions, or the marginal conditions, read that if you sum over one index, you get the first measure, and if you sum over the other index, you get the second measure. So it is literally a linear optimization problem with some equality constraints. So very complicated to solve. It's a linear programming problem when you have many points of discretization in your measures. So the computational complexity is very big. And also there are some overfitting issues when you solve the problem exactly, because we know that from linear programming that the optimal points are situated on the edges of your convex polytope that gives your marginal conditions. And if you move your marginals a little bit, then the solution of the problem will change significantly. So what can we do? Is another approach that I'm generally using or we generally use in our group, is to solve some different problems and take a limit. So you have this problem that is linear and is very nasty in terms of solution, and you want to solve something similar that it's actually approaching it. So it's like it's similar in terms of a function. It's a function that is very close to this one, but you also want to show that the minimizer of your function that you're trying to solve is also approximating the solution of the original problem. So what we are trying to do, we are adding some convex regularization, and one of the nicest example is to add some Shannon entropy. So we fix some small parameter epsilon, and we add some term that is convex. And in this case, it's like the released Shannon entropy. So what you can see right now, so that the function here, the base function is the same, but we also add some epsilon plus a convex term. And when like the intuition is that when epsilon is very small, you actually approximate your original function. So
it looks like a Monch-Kantorovich problem, yeah?
Well, so like this one without the entropy term is the Monch-Kantorovich problem.
All the problem when you add some functional to the usual cost functional for Wasserstein distance, for example, it looks like Monch-Kantorovich problem. Yes.
No, the Monch-Kantorovich problem is not described in terms of like you don't have entropic terms. You only have the.
We have this, and we have the distances which we look for the mapping. Yes, which maps one measure to another, and we want to minimize the distances, and we can add some quadratic function also, but not of course of such kind. Yeah. Here you still don't have any mapping. You just playing with these probabilities. Okay. Mm-hmm.
Yeah, but the only problem is like it cannot be the Monch-Kantorovich problem, because the solution that is of this problem will actually be in the interior of the convex set. So it is never a map. So I will show the picture later. So it actually can never be a map. So it can never be a Monch solution, because also for if you take the entropy of the Monch map, or like the probability that gives you the Monch map, it will give you the plus infinity of the entropy. So this one is the approximation, but when you send epsilon to 0, you will approach to the Monch map. So I will show it in the picture later. So as I mentioned before, so this problem is now convex because we add the convex term, and we can say that since it's a convex problem, we have a unique minimizer, so which is kind of nice. Then there are nice numerical methods that you can estimate this solution. So you can take some gradient methods, or you can also use the so-called dual approach. So for optimization problems, very often you have the primal problem when you want to minimize something, and you have the dual problem when you want to maximize something. And these problems are actually overlap at some point where these two actually coincide. So if you're taking the approach using the maximization of the dual problem, typically you can use some alternate maximization, and it defines a very nice algorithm that is also called Sinkhorn algorithm that is known to converge very nicely. So, but also what I wanted to say next is that the approximation of the solution of the original problem can be obtained by approximating the solution of this problem. So when you're solving this one for small epsilon, you will actually also solve or almost solve the original problem. And
Nataliia,
there's also
Nataliia, excuse me. So we have this statement that the solution of this so-called entropized model comes to the solution of initial model without any restriction on the cost function. So
No, typically we need.
There are no any additional conditions. Yeah?
No, for this example, it's a discrete example.
Yes.
Everything is bounded, everything is nice. But in general, there are some nice results for like continuous bounded function, and also we usually, or at least the lower semi-continuous bounded from below functions. So like there are some several assumptions, but I'm actually working more on quantum optimal transport, and we so far are working with finite dimensions, so we only use something bounded. And then we want to try to do some more like general case, for example, maybe go to infinite dimensions, but it's something that I'm going to mention in the end.
Okay.
Okay, so there is also a physical intuition for this problem. So like, as I mentioned before, so there are, say, these problems can arise in, for example, quantum chemistry, and this epsilon times entropy can be so-called like the external noise that is coming from the environment, so that the epsilon is the temperature of the environment, and the entropy gives you like the noise. And let me show you a little bit the idea that we can very easily see in the discrete case. It actually looks very similar when you take just general measures that are with the integrals, but in the discrete case it's very simple. So since it's a convex problem, we can form a Lagrange function and introduce some Lagrange multipliers that contain our marginal constraints, so that we have the sum minus the marginal conditions are equal to 0. And by solving this Lagrange the partial derivative with respect to the pi ij, we can get the unique minimizer that has the shape of the Gibbs kernel. So it's the exponential of u plus v minus c divided by epsilon. So in fact, so this is really how the solution would look like. But so I will mention later in the slides, but at some point, see, when epsilon is becoming very small, this is becoming very big, but in such a way that it still somehow integrates to 1. So another perspective is really that the ones that satisfy this Pij is equal to this exponential are actually the maximization points of the dual functional. So as I mentioned before, we have the primal functional that we want to minimize and the dual functional that you want to maximize, and there is some intersection point, and this relation is given by this expression. So let me show you some plots. So this is the example when we have some mixed Gaussians, and that is solved numerically for some different values of epsilon. So when epsilon is very big, somehow the solution becomes like the solution of the problem when you want to maximize the entropy or like minimize the minus entropy. So in fact, it is becoming very chaotic, and the solution actually looks like a product measure. However, when epsilon goes to 0, you see that the solution actually starts looking as a graph or like as a map. So it's really is like a Monge map. So we know from classical theory that in general, the solution of this optimal transport problem will form you a map that actually gives you like, well, you take one mass from one point and you send it to another point. And there are some general gamma convergence results and related to these, so that the solution of this regularized problem, as epsilon will go to 0, will actually approach the solution of the original problem, the one that we had before, so the one that does not have the entropy at all. And of course, since this also the minimizers converge to the minimizer, also the minimum value of this new problem will converge to the minimum value of the other problem. And also, as I mentioned before, that in fact, for any epsilon, these solutions of the regularized problem will always be in the interior of the set, so it's not really on the edge. Okay, now let's talk a little bit like what is quantum optimal transport, and this is a very fun topic. So in here, it is somehow the generalization of probability measures, but for the quantum states. So in the quantum physics, we usually work with some Hilbert spaces and with some operators on Hilbert spaces. And so instead of measure spaces, we will have Hilbert spaces. And now, instead of probability measures, we're going to work with the quantum generalizations of probability measures, which are also called density matrices. But in fact, these are just operators on Hilbert spaces that are semi-definite positive and have the trace that is equal to 1. So it's a sort of a operator analog of a probability measure. Now, also for the sake of simplicity, we're going to consider, so on the left, we had the cost function that was just a bounded cost function. And in the right-hand side, we are going to consider its analog, bounded operator, or a Hermitian operator. So it's Hermitian means bounded self-adjoint. And the set of marginal constraints. So in the first case, we had the projections of your measure to one space are the marginal measures. And in the quantum case, we have something similar. So here we will be working on the operators on the tensor product of Hilbert spaces in such a way that if you project this operator on one space, you get the first operator, rho, which was like the first marginal. And if you project it to the different space, you get the second operator. And the projections is sort of like the partial integrals. So they all called partial traces. So if you have an operator on the product space, then you say that its partial trace is equal to something. If for any other operator that you act in it, you actually get the identity. So if I take, so basically this is considered in the distributional sense. So you have your operator gamma on the product space. So it's a double integral, or like the double trace, and it's equal to the trace on the smaller set. So here we have a trace on the h times h2, and here we have the trace on h1. So it's sort of a generalization of the partial integral, but for operators.
Excuse me, can you give us an example of such pairing? Because for measures it is easy to understand, but here how to construct at least one such example of such operator, because you need this trace gamma 1 multiplied on any j.
Yeah, exactly. So the typical example is very similar to the example on the products in these joint redistributions. So we know that one of the possible couplings is the product measure.
Exactly.
In this case, you can take the tensor product of rho and sigma, and this is one of the examples. So you take the tensor product because both of them have trace 1. You integrate over 1, or like you take a partial trace over rho, you get something times 1, and you get sigma. Or like if you take, so it's the example.
But for example, if they're equal, then can we have some other example, like what we have instead of the diagonal? Because in case of measures, when we have two equal measures, then we can concentrate coupling on the diagonal, yes? What is here the analog of the concentration on the diagonal? When they are equal, what is...
So are you talking about the diagonal decomposition of the operators?
No. Suppose that H1 is equal to H2 and rho is equal to sigma. Then can we have another example on that operator C, which is will be similar to the measure concentrated on the diagonal to reflect the equality?
Actually, yes. I will give you an example. So as I mentioned here, so you have, for the classical case, you have this form that is exponential of u plus v minus c over epsilon for some u and v. In fact, in the quantum case, it can be also generalized. So there will also be an exponential of some operators. So there is like the direct sum of operators. But let me move on.
It can be constructed, yeah?
Yes, it can be constructed, actually, yes. So there are some results also by my supervisor and the collaborators and some current work that we're working on. Okay, so this is the quantum optimum transport. So the problem can be defined in a very similar way. So like the quantum Kantorovich problem can be defined as the infimum of the trace of the C gamma. So in this case, we just substituted all sums or integrals with the traces, and we had measures or functions. So now we just substitute with some operators and the marginal conditions given as before with the partial traces. So there are several examples. I'm not going to mention these because I have like 4 minutes. And yeah, so there are examples in quantum information theory and also in quantum chemistry. And so this is like the typical cost functions that we would be interested in to solve like quantum optimal transport problem for something that is in quantum information theory or in quantum chemistry. So these problems exist. And let me first also mention the nice result that is also obtained by my supervisor. So we can also get some convex regularization. So with the example of the von Neumann entropy, here I'm giving the exact example as was before. So we had like just the Shannon entropy. Here is the quantum analog, which is the von Neumann entropy. So we have this convex term. So the advantage is also that the problem becomes very convex, and there we have a unique minimizer. Then we can also take some variations and examine how the solution will look like, and also examine the dual problem and so on. And the similar is the situation is with this new joint distribution, which is like the joint density matrix. So it also lies in the interior of the convex set that has the correct marginals. And it was also given by this exponential of u plus v minus c over epsilon. So here u and v are the solutions of the corresponding dual problem. And you can also think about these as the Lagrange multipliers, as if you construct the Lagrange problem. So this is the other example of the possible gamma that satisfies it, but it has to hold only for the solutions of the dual. But there are technical complications that we cannot really do a lot of stuff because it is non-commutative in the sense that the exponential of a plus b is not equal to the exponential of a times exponential of b. So when you take some numerical schemes, you cannot really compute everything easily. You have to solve a operational problem at each step when you take the iterations. And here is something that I want to mention. The last thing is what is my research about. So instead of taking some entropy that has the form like x log x minus 1, we can consider a general convex function. So you take a convex function, you lift it to the operator case, so that you're using the functional calculus, and you consider the problem that has like epsilon term times this convex entropy. And what is nice that we also already proved with my collaborators that yes, the minimizer of this exists, and also the minimizer of this problem will converge to the minimizers of the problem before. Also, what is very nice is that if you take some general convex function, for example, x squared in terms of matrices is much simpler to compute. Instead of taking an exponential of matrix, you just take in the square of a matrix. So you don't have to diagonalize the matrix to, so it's very nice for numerics. But another important thing that we are working on is the relaxation of the marginal constraints. So instead of having the constraint minimization problem, we can relax it by introducing some functional that is growing very fast when our marginals are not correct. And we instead start to consider the problem over all just positive operators instead of taking the ones the correct marginals. And there is some interest with ongoing work. I'm also very happy to discuss with some people if they're interested. I can give you my email address. And I'm very sorry I'm running out of time. So also thank you very much for inviting me to give a talk today. I'm very happy to see some people that I already saw before. And I'm actually quite excited that got the invitation. Thank you very much.
Okay, thank you very much for interesting talk. And of course, there are several questions maybe if you send your email, I will ask you, because here we have no time, unfortunately. So I have to announce next speaker. Thank you very much again. Okay, and now next speaker is Igor Chulakov from Taras Shevchenko National University with a talk on generalized Skorokhod map for piecing together two processes. Okay.
Good evening, everyone. So here you can see the topic of my talk. Andrey Volodymyrovich Skorokhod formulated the reflection problem in his work in 1961, which proved to be an effective method for constructing reflected diffusions. Based on this reflection problem, a mapping was built that assigns to a function the solution of Skorochod's reflection problem for that function. This mapping turned out to be useful for solving various problems in Q theory. Skorochod's reflection problem has been generalized by different authors. In particular, Andrey Pilipenko in his article posed the problem of jump-like reflection, and this work made it possible to construct Brownian motion with jump-like reflection. In their common article, Pilipenko and Sarantsov considered a system with switches, and as a result of certain limit transitions, were able to obtain in the limit the classical Skorokhod reflection, reflection with delay, absorbing reflection, and reflection with jump-like exit from the boundary. Let's consider the next task. The following problem. Let's f and g be two continuous functions. We want to construct a dynamics whose increments coincide with the increments of f in the upper half plane and with the increments of g in the lower half plane. To do this, we first introduce a level delta and consider a dynamics with switches that happen when certain levels are reached. Specifically, we start with the dynamics of f at time t equals 0, and when ft falls into the interval from minus infinity to minus delta, we switch from the dynamics of f to the dynamics of g. Then we switch back to the dynamics of f when it falls into the interval from 0 to infinity. Next, we switch back to g upon reaching the level minus infinity, minus delta, and so on. The function constructed according to these rules we denote by y delta. Our next goal is to let delta approach 0 and find the limit of the switching dynamics y delta. On this picture,
excuse me. Am I understand right that you want to define such a dynamic starting from any point of the real line? Simultaneously.
No, we start from the upper point.
So you just fix one starting point and then looking what happened with this point, yes?
I think if I understand you correctly, you mean about the first point. We have some restriction on the function f. F0 should be greater than 0. That's okay. The only restriction.
Yes. So you have just one starting point, yes?
Yes.
Okay.
It's now it's fixed functions. Here on this picture you can see the example of this problem and its solution. The functions f and g are given, and using them we build the dynamics y delta. Let's see how exactly it is built. First of all, we start exactly like function f. Here our function y delta and f coincide exactly. But then we hit the level minus delta. And here in this point, we make a switch and switch to the dynamics of g. And from this point, our dynamic y delta behave itself like g, but a little bit shifted. Then we go up and reach level 0. The level 0 is also the level where we make switches. There are two levels, minus delta and 0. So we make a switch to our blue function f. Our dynamics behave itself like f. Here you can see it's the corresponding parts, and so on. In minus delta, we again switch to the red function, you can see corresponding parts here in and it's in y delta, and the same piece of the graph for function g. And so on. When we reach level 0 blue function, use our last piece of the left branch of this parabola, and so on. Switch again to red. To red regime, reach here, we use our right branch of the parabola, and from this point we will never reach 0. So there are no any switches from this point. So here how this dynamic is built. On the next slide, next you can see actually the same problem, but here we tend delta to 0. Here we want to tend delta to 0 and see what we will have in the limit. Let's consider a similar problem that would be a little bit more symmetrical with switching regimes. Let f, g be two continuous functions again, and delta greater than 0. Let's build a new dynamics. We start with the dynamics of f at time t equals 0, and when ft reaches level 0, we take a delta jump down and switch from the dynamics of f to the dynamics of g. When we reach level 0 again, we make a delta jump up and switch from the dynamics of g to f. Next, we switch back to the dynamics of g upon reaching the level 0, and again, this switching happens with a delta jump down, and so on and so on. Let's again denote final dynamics as y delta t. On this picture, you can see example. On the left picture, it's our input functions. On the right picture, our final dynamic. So what's the difference? Here we make jumps in both cases when we reach level 0. Previously, sometimes it was level 0, sometimes it was level minus delta. Here it's more symmetrical from this point of view. So we, when our blue function f hits 0, we jump down by delta, where our red part of our dynamic y delta hits 0 from below, we jump up by delta, and continue so on by switching between regimes f and g, between blue and red regime, and also here we have jumps. In our previous problem, there was not any jumps. Let's fix continuous functions f, g, and the level delta greater than 0. Denote by y delta the solution of switch problem for functions f, g, and level delta. It's the switch problem that was introduced first. Then let's denote by f tilde delta the next function. It's f, but shifted by delta up. Denote by y tilde delta the solution of the switching problem with jumps, our second problem, for function f tilde delta, g, and level delta. We can notice that functions y delta and y tilde delta are pretty similar, and the next inequality holds for every t. Really, let's see, and we will really see that they are pretty close. On the left, again, our input functions f, g, but here we also have new function represented by green color, f tilde delta. Delta, as always in this presentation, it's 1. So f tilde is f, but a little bit shifted up. And on the right picture, by blue and red colors represented function y delta, the solution of our first problem, and by green and red colors represented function y tilde delta, the solution of our second problem. So we can see that in the red parts, when we use dynamics g, they are exactly the same. Exactly. And in those parts where it's not red regime, they are close. This interval between them is exactly delta. So holds the inequality y delta minus y tilde delta less than delta. From the examples, we could see how a solution of switching problem is built. When we build dynamics with switches, either with jumps or not, as a result, we have a dynamics which increments coincide with f in the upper half plane and with g in the lower half plane with an accuracy of plus minus delta. It's natural to assume that when we let delta tend to 0 in the solution of switching problem, we would obtain in the limit some dynamics that combines function f and g in a natural way. We obtain the inequality y delta minus y tilde delta less than delta. It means that if there exists some function y such that y delta tends to y when delta tends to 0, then we also have that y tilde delta also tends to y, and vice versa. In other words, the switching problem and the switching problem with jumps introduced earlier are equivalent with respect to the limit behavior of their solutions. Let's generalize the switching problem with jumps. Let p be a fixed number from n, let xi be a continuous function from r plus, for I equals from 1 to p, delta greater than 0, and also we will have some vector ai, where ai greater than 0 for all I. We aim to build a dynamics on Rp in the following way. We start from the point 0, then we begin to move on the axis E1 as the function x1. When x1t hits 0, we switch to the axis E2 and make a jump on the second axis, and the size of this jump is exactly A2 multiplied by delta. And begin to move on this axis as a function x2. When x2 hits 0, we make a jump on the third axis, the size of the jump A3 multiplied by delta, and begin to move on this axis E3 as a function x3, and so on. And in the end, when xp hits 0, we make a jump on the first axis, the size of the jump a1 multiplied by delta, and begin to move on the axis e1, again using function x1. Here, let me try to draw it, how it will look. So we actually start from the point from the point 0. Not from the point 0, from the first axis, and we begin our dynamics behave itself like function x1t on the axis, on the first axis. So we start on first axis and we move on this axis, move here, here, here. But when first happens that we hit 0, in this point we make a jump on the second axis. Jump a2 multiplied by delta, and from this point we start to move as function x2. Again, we can move here on this axis, move until the point when we hit 0, and here we make jump on the third axis, jump A3 multiplied by delta, and here our dynamics will behave itself on the third axis like x3. And the last step, we move here upon we reach 0, and we return to the first axis where we stopped in 0, but also make a jump a1 delta, and so on as the cycle is. The cycle is closed, and this story will continue again and again. Let's denote the final dynamics as y delta again, but here we add the notation that actually now y is a vector. Now it's a vector in Rp. We can write the vector function y delta in the following way. Where the function ti delta represents delayed time for function xi, the time freezes for function xi when we leave the axis ei. And the function si delta represents the sum of jumps made by time delta on the axis ei. On this graphic, you can see how approximately would look like functions of time ti delta and functions of the jump si delta. So si delta, as expected, it's a jump function, and this jump always will have size ai delta. Always it's the same. And function ti delta, it's shifted time, it's continuous, and sometimes it grows like just function t, and sometimes it freezes and it's constant when it freezes. As previously, we aim to tend delta to 0 and obtain some natural way of combining dynamics x1, x2, and so on xp. But we can notice that in formula for y delta, the delta is present only in functions ti delta is si delta. Really, take a look at this formula, and you can see that here we use delta only in functions ti delta, si delta. So it is sufficient for us to investigate the limit behavior only for these functions. As you could see, this new problem cannot be visualized very well in space RP. To work around this problem, let's draw each part of our final dynamics on the Cartesian plane and represent each axis by its own color. Now we can think about our final dynamics as a function on R, and now it's much easier to visualize it and think about it. Here is the example for p equals 2, but p can be any number, 3, 4. It depends from how many colors you have. Here I have 2 colors, so p equals 2. And delta is usually 1, but the size of jumps are different. So when for our first functions, jump will be 1. For our second function, jump will be 2. X1, X2, our input functions. Let's see how built our final dynamics. We start as X1, we hit 0, we made a jump up by delta multiplied by A1. So now it's just 1. We switch to red regime, hit 0, make a jump A2 multiplied by delta. Now it's 2. Continue to behave like function X1, and so on and so on. You should notice that here, when we switch from blue regime to red regime, we make jump 1, and from red regime to blue regime, we make jump 2. So the jumps are not necessarily the same. Let's consider case p equals 1. Denote a1 multiplied by delta as delta, because we now have only one jump. To simplify the notations, there are no functions except x1, so there is actually no switching. But there are still jumps when x1 hits 0. It's the simplest case because without switching we have no shifted time, and the function t1 delta equals t trivially. Let's fix any t greater than 0 and consider our problem on interval 0t instead of r plus. It's not difficult to see how y delta is connected to x1, and we can express moments of time when y delta makes jumps in terms of on function x1. Let's denote tk as the first time t when x1t reaches the level minus k delta. Let's see its own example. How it would look. So you can call it x1. So we hit 0, but because there is no any function for us to switch, we just make a jump. And our final dynamics, our original function, but a little bit shifted up, and so on. Again, we hit 0, we make jump up, and continue to move. Even can understand how function y delta and f is different. On first step, the difference between them is exactly delta. After the third jump, it's exactly 2 delta, and so on. 3 delta, 4 delta, so on and so on. There can be only finitely many points, and it's not difficult to notice that tk are the moments where y delta makes jumps. Let's consider the next function, m1. We denote by m1 the next function, and we will call this function the running minimum of x1. For any t from this interval, there exists such k that t belongs to this interval tk plus 1. That means that S1 delta t equals chi plus 1 delta. And that also means that the function x1 has already reached the level minus k delta, but has not reached the level minus k plus 1 delta yet. Thus, we have m1 t lies in k delta, k plus 1 delta. This means that the difference between jump function and this running minimum of x1 less than delta. And this means we have S1 delta tends to M1 when delta tends to 0 in the space of continuous function. And finally, we have that our solution of our switching problem tends to x1 plus its running minimum. And let's summarize. We have investigated the boundary behavior of solutions of switching problem when p equals 1. Now we know that the limit function exists, and we have found an explicit formula for the limit function. The formula turned out to be really simple. It's the sum of function x1 and its running minimum. It's just the time to notice that we could have seen this formula somewhere else. So here I should recall what is it, the Skorokhod reflection problem. Here I have its definition and example and theorem about existence of its solution, but I'm afraid I have not time to recall it properly. But what we should pay attention at that we have explicit formula for the solution of Skorokhod reflection problem. And actually, this formula looks like we take our original function f and we should add to it its running minimum. Now we can assert that we got the solution of Skorokhod reflection problem for x1 when we were investigating the limit behavior of switching problem with p1. We have there the same formula, function plus its running minimum. Let's return to the case when p greater than 1. Here is a recall of how our function looks like. Our dynamics with switches, and we can find some formulas for our functions of shifted time, ti delta. Here you can see them. There are two inequalities and one equality. Yes, here is again an example of this shifted time function, and we can find this lemma. For every e, the set of functions ti delta satisfies the conditions of Ascoli-Arcellas theorem. We can use the Ascoli-Arcellas theorem, which grants us the following statement. For all I, for all sequences delta n, such that delta n greater than 0, there exists some function ti continuous, and some subsequence nk such that ti delta nk tends to ti in the space of continuous functions. If we would be able to prove that, these functions ti is the same for all sequences delta n, then we will prove that ti delta tends to ti. Working through this problem, we got the following inequalities for functions si delta, ti delta for all ig. Here you can see them. The second from them is actually pretty obvious. We made a limit transition in those inequalities and obtained the following system for the limit functions ti for all ig. Here you can see them. If we will find some conditions of functions xi, such that this system of functional equations will have the unique solution in functions ti, then it will follow that that in the space of continuous functions, ti delta tends to ti, where the functions ti are the unique solution of the system from above. And after that, we will have from inequalities that we mentioned earlier that si delta tends to mi ti, and thus we will obtain the limit function for the solution of switching problem with jumps when delta tends to 0. And here I want to present you some result that we have for case p equals 2. the theorem: if the functions m1, m2, running minimum of function x1 and running minimum of function x2 have not any common levels of constancy on 0t, then the functional system, this system, has the unique solution in functions t1, t2. That's all. Thank you for your attention. I'm waiting for your questions.
Okay, thank you very much for interesting talk. And before we start other questions, let me ask you, there is such article of Lejean and Raymond devoted to exactly the same construction when we have two Brownian motion. One is used as the upper half plane, and another one is the negative half of the real axis. Do you know this article?
No.
Please have a look. They construct the solution, and they discuss the dynamics which start from any point of the real line. So they discuss what is the mutual behavior of the different points. So maybe it can be interesting for you. Okay, maybe some other questions, comments, please.
So I would like to say one short comment that our aim was to obtain analog of Skorokhod reflecting problem for skew Brownian motion or for Walsh Brownian motion when we pass together different Wiener process or just diffusions. And we would like to get such processes as the application of continuous mapping theorem. So our dynamics will be different Wiener processes and some switches between them, some exits from zero, and the map we get, it is continuous in supremum norm. And I hope that we will be able to get a lot of interesting limit theorems for perturbations of such type.
Okay, thank you very much. Please, other questions? If not, I must to thank all our speakers today and mention that all of you will get the certificate about this international conference. And I wish you success in your mathematical life. And as I said to every of you, I am waiting for your 1 hour regular talks at our seminar Malявin Calculus and Applications. This is the last session of our seminar in this semester, and I ask all participants to send to Georgi the propositions of titles and abstract of the talk on the fall semester. Thanks everybody, and bye. Have a nice summer.
Yeah, bye.
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 Bye.